So good morning, good afternoon, everyone. Thank you for being here. And welcome to the John Crane webinar entitled Discovering the Synergy Between Filtration Systems, CFD Simulations, and the Evolving Energy Market. I am Elsa Gandu, your North America Marketing Manager for John Crane.
And I am Brian Shackelford, representing the eChem Expo.
Excellent. Just before we begin, just a few housekeeping notes. Our discussions will be guided by subject matter experts Brian Adamson and Paul Hume. This session is live, but everyone will be muted, so please mute yourselves. We will open it up for questions after the presentation, going live with Brian Adamson for direct Q&A. This is being recorded at this time. The webinar is accredited for PhD credits per Tennessee standards. If you're outside the state, oh, I'm sorry, Brian, I think that's your line. Apologies.
That's okay.
Sorry.
I'll back up and just remind everybody that
Okay.
today's John Crane webinar is actually in collaboration with eChem Expo. And eChem Expo is, as I mentioned earlier, for those who were already with us, the #1 multidisciplinary applied innovation event in the process industry. We're celebrating our 25th year. We are, in fact, having our live event April 17th and 18th in Kingsport, Tennessee, and we hope you will join us there. And then I'll jump ahead to the PDH accreditation that is per Tennessee standards. If you're outside the state, please verify with your local professional development board and confirm that the course here is applicable for your own credits. And do please remember that PDH credits are auditable and may not be claimed for simply watching the recording of the webinar. Not that anyone would ever do that, I understand, but just keep that in mind. And then Elsa, I'll turn it back over to you and we can get started.
Let's dive in and introduce our speakers. So let's start with Paul Hume. Paul Hume is experienced in polymer melt filtration, serving as our John Crane North America Business Development Manager. Some of his past roles include 10 years at Baker, 11 years at Prover, and 5 years at Whatman. He holds a degree in mechanical engineering and marketing from various institutions. Brian Adamson. Brian Adamson has vast experience in rotating equipment filtration as John Crane's Filtration North American Business Development Manager. He's been with the organization for 15 years. That includes 11 years at Indifil and then 13 years at Farley Arlon, with 4 years at Hydrene Hydraulics, and holds an associate degree from Gateway Technical College. And with that, I'm going to go ahead and stop sharing and give it over to Paul. Thank you.
Thank you, Elsa. So I'm going to start the presentations, and the first one is going to be on CFD for polymer filtration. So just give me a second while I'm going to knock the camera off and share my screen. So just a little bit of background before we actually get into the presentation is that John Crane polymer filtration is an aspect of John Crane that was acquired back in 2018. We have design, engineering, and manufacturing capabilities, and we have 4 different locations where that takes place. You can see on the screen Germany, Czech Republic, Netherlands, and India. And we do the whole kit and caboodle of the polymer filtration, so everything from elements, small systems, to the very large duplex systems used in virgin polymer plants. So let's dive into CFD, computational fluid dynamics for non-Newtonian fluids in filtration. So we're going to understand the functionality of a polymer filtration utilizing this tool, and it'll enable the design optimization and give proof of concept. So I'm assuming most people are familiar with what CFD is. The beauty of what we offer here is we took an Autodesk program and we altered it to be able to not only do what it could already do non-Newtonian fluids, but it couldn't do them in filtration. It could only do non-Newtonian fluids through pipework, and you may be familiar with that. But what we have is a unique version, self-designed or self-improved by our former owner, Dr. Thomas Grimboschbach. So, as I mentioned, the result of the CFD, if we do it, for instance, on an older system, if we run an analysis on an older system, the result is going to be a report. And that report will give you a very good understanding of what can be optimized, what the cost of that optimization is going to be, and therefore lead to your understanding of your investment risk. So the report is a great tool to use for proof of concept, for improvements, for senior management. So the engineers can utilize this and show that, hey, if we make this improvement, it's going to be very useful for, and you can see the costs here. So it's going to be totally understood by senior management. What we need to understand in doing the analysis are things like the pressure drop, the flow, the temperature, viscosity, shear stress, residence time, all the typical aspects you would have with a polymer filtration process. What we do ask when we first start looking into this on behalf of a customer is for some information about the process. Obviously, we're going to. Ideally, we can get we can get CAD data. That's great, but if we could get drawings of the systems and elements, that's very nice to get and makes life pretty easy. Worst case scenario, we can work with sketches and perhaps a sample of one of your filter elements, and we can run with that to be able to create the model. We also need, obviously, the process data and the rheology curves, particularly of the specific polymer we're going to be modeling. We can do more than one model, so if you're running various different polymers through one system, we can model for each different polymer if that's a need. We also have in our database quite a number of polymers that we've already modeled. Now, those are probably unlikely to be exactly the same as you've got. We know that from experience. There's so many different variants that our customers use. It's very unlikely that we've got the exact polymer in-house. But if we have, then you don't need to supply the rheology data. We've already got it. As I mentioned before, one of the key aspects of, or the key aspects of our CFD modeling is that it's unique. And the reason why it's unique is we can model it for filtration, in particular, the filtration media. And so understanding how that filtration media is going to perform and what characteristics is going to impact on your polymer as it's passing through the media. In order to do that, you need to understand what the media, how it's comprised. A lot of the filter medias used in polymer filtration are metal fiber type filter medias, and those are typically most commonly supplied by either Paul or Beckart. Beckart's a former manager of Beckart. But we have Paul, Beckart, and other metal fibers and wire meshes, Dutch weaves, optimized wire meshes, beta meshes, etc., all programmed into this modeling. So we understand exactly how these medias are made up and what impact they're going to have on the polymer. And they all do have a different impact on the polymer, not just in micron rating, but different media types within the same range. Say 20 micron, but say a Paul 20 micron XYZ might be different than a Beckart 20 micron ABC, and we need to understand that. So gives it a uniqueness to John Crane. When we start setting up a model, the first thing we've got to do is try and find a symmetrical portion of the system, and it's really the smallest symmetrical portion, because this whole modeling takes up an enormous amount of computer space and data required to be able to do it. So the smaller we can actually get that symmetrical chunk of the system, if you like, the quicker and easier it's going to be to calculate all the data and come up with the report. So as you can see here, I'm showing a slice, like a three-dimensional slice through a filter system, and this is a symmetrical piece. Maybe this looks like something like a 30 degree slice, really. So we could get what, like 12 slices of this exactly the same in a system. It's very rare we get a non-symmetrical system, but we have had them where we had to calculate the complete vessel. And actually, when I think about it, one of them is a former Eastman systems, where we actually did have to use the whole system to calculate it. So yeah. Setting up the model, as far as meshing is concerned. So again, if you're not familiar with this, what we have to do is put a mesh over the whole system, the whole internals, and that mesh is a three-dimensional mesh, of course, and it varies in its nodal density, if you like. So the nodes are the points where where you can see the lines cross. And where we need more information, where it's really pertinent and important to gather that information, is going to be in and around the actual filter element itself. In the more open areas of the vessel, yeah, it's not going to differ from one small area to another small area very much. But when you look at the actual filter element itself, we're going through all these different medias, and there's a lot going on just in the area where the pleat pack is, for instance. As you can see here, how dense those nodes are compacted around the pleat pack. So it's important that we mesh this correctly. It tends to be different. So unless you happen to have 10 similar systems just with different elements, for instance, then we have to do the meshing from ground up every time. It's not usually possible to just use an old mesh. So this takes up quite some time when we're doing the modeling report. The rest of the time is taken up by the actual data crunching. At the bottom of this slide here, you can see running parameters. And it usually means when we're running a report, there's going to be between 50 and 300 million nodes of data. And each node can require 4, 5, 6 sets of data, depending on what we've determined to be the outcome of the report. Running so much data requires a lot of computer power. So we invested, this is another part of the uniqueness, we invested in a very large server in order to do this. You've got all the details up there on the screen, but basically for the layman, that's about 400 times a regular laptop's power. So it's a huge system in order to do this. And using that system, it still takes us, on average, around 7 days to compute the whole thing. One of the reasons is, you can see we've got 50 to 300 million nodes. We've got to go backwards and forwards on this, so that we actually calculate it forwards, calculate it backwards. It takes 30 minutes every iteration, and we need around 300 iterations to get accurate results. It kind of becomes more and more accurate the more iterations you do, and we run about 300 before we're satisfied we've got a good accuracy. I'm going to run over some customer examples just to give you an understanding of exactly what this is capable of. So the first one is going to be where the customer is looking to increase the polymer throughput without changing his vessels, without actually changing his filter candles as well. And with, it's not written here, but I know he had one additional requirement that he was running, I think this was 10 micron system, and he wanted the ability every now and again to run this at 5 micron. The problem was that with currently, when he'd actually tried it, he really couldn't get anywhere near enough on-stream life to be able to do that with the current system. It meant if he wanted to run 5 micron, he would have to buy a complete new system. Then the second one's going to be a customer who had gel contamination in a film, a battery separator film, and he wanted to understand where those gels perhaps were coming from and what he could do about it. So the first one, just so you understand, you're going to see some color-coded slides. These color-coded slides are going to be for flow, velocity, viscosity, and shear rate that you're going to see. Here's an example of one, and you can see we've got a pipe coming into a filter vessel and a pipe exiting a filter vessel. This is a flow velocity diagram, and you can see we've got fast flow coming in, indicated by the orange and reds. It enters a large vessel, so consequently slows down, and that's indicated by the fact that it's blue, and then exits through the pipe again and speeds up. So you've got the scale on the right-hand side to give you an indication. And we utilize these in the report. So when we provide the report, everything's color coded to make it very easy to see. You know, it'd be a lot more difficult if you were just looking at tablature and numbers. This makes it very easy to actually understand what's going on and interpret the results. So first objective, increase polymer throughput within the current vessel constraints. So what we see here is a before and after picture of a cross section of the filter system that we analyzed or simulated. And you can see on the left-hand picture, we've got a lot of dark reds and deep blues. This indicates a big differential between the flow distribution, with the flow distribution. Ideally, on this color coordinated diagram, what we're trying to see is the colors merge together as best as possible. That will indicate that the flow rates are becoming very, very similar, and that's what you're shooting for when you design a better flowing polymer system. So this indicated that he did have a poorly designed layout on his tube sheet, because if you remember, all we can change on this, we can't change the vessel diameter, length, we can't change the candle diameters, can't even change the filter area on the actual candles themselves. So all we can play with is this tube sheet layout in this instance. The right-hand one shows what happens after we've done some modifications and redesigning. And on the redesign, where we've put 15% more media in the fact that we've adjusted the location of all the filter candles and managed to squeeze in an extra, I think it's 5 in this, that ended up with 15% more additional area. But the key thing here is the spacings between the filter candles have to be as even as possible. That's one of the tricks of getting the filter to flow with even flow distribution. And if we look at what happens with the shear rate after we've made this change, you can see here that because we've moved to a more sort of even green, light blue situation than the deep blue, bright blue situation we had on the left, we've got an easing of shear stresses. And this is borne out by the viscosity profile. And you can see on the viscosity profile how the viscosity is we've got much less shear thinning going on in and around the filter elements, as you can see from the two different shots here. And you can see on the left hand one how dark blue, that's low viscosity, we have in and around the filter elements, whereas on the right one it's more of a green color. So we have got a relaxing of the shear stresses and a less change in the viscosity as the polymer passes through the filter elements. Again, desirable and helps with the throughput. So when we showed this to this customer, he expressed interest, but as he was one of the very first customers we'd ever dealt with, he wanted a little bit more. He wanted to trust us a little bit more, I think, on it. So what he suggested was, well, I'll go away and I'll run a regular filtration process, and I'll make some measurements and feedback to you. And in the meantime, you guys run the CFD for 3 different scenarios, which was pretty much beginning, middle, and end, and then we'll come back and compare notes. And that's what we did. When we got back together, our points pretty much paralleled his actual real-time run. However, there was a 2-bar differential. We did understand pretty quickly what the reason was. It was because when we take our measurements in theory, we're actually only doing it from the inlet and outlet, absolute inlet and outlet of the filter system. Whereas in reality, his pressure transducers were down pipes and around bends, both on upstream and downstream. So we had to calculate what the pressure losses were through those pipes. Came out to somewhere around 2 bar. So that meant when you took that 2 bar into account, we were virtually mirroring his real-time data. So that gave him the confidence to go ahead and make the changes. He did the redesign. And after installation, and I did mention we managed to put 15% more area in, but there was all the other changes that we made up to the actual location of all the filter elements to make sure that the distances between them were as equal as possible. He reported a 35% increase in on-stream life. And in addition to this, it meant he could actually get a reasonable runtime by putting his 5-micron filter elements in. As he reported this afterwards, he said he got a reasonable runtime, which meant he didn't have to go and buy a new filter system just for one polymer that needed 5-micron filter elements. So that was a big result for him. This second one, the objective was to remove gel contamination for battery separator films. So this was a small system, 7-candle filter system, as you can see here. What you're seeing now is just a cross section of, in the top left-hand side, you can see one filter element and half of another one inside the filter vessel with the inlet and outlet pipes showing with the fast-flowing red flow. One of the beauties of this system, our modeling, is we can zoom in. And so on the 0.007 scale, as it indicates there, you see a certain color distribution. When we zoom in, we can get more information about what is actually going on. So on the right-hand picture, you can see on the 0.002 scale, we've got some very dark blue, which means slow flow in the corner, as indicated by that black circle. This is a dead zone. What's happening there is that polymer is sticking to the actual vessel because it's moving too slow, and it's sticking and carbonizing, and then it's attracting more polymer to stick to it. And what eventually ends up happening is it kind of builds up in the corner there, and then as the polymer sticks to it and starts to change in viscosity, because it's now big enough, this area, it's stuck into the faster flowing area, and then it sloughs off polymer. But it's a more viscous version of the polymer, i.e. it's a gel, and so then it sloughs off a gel, and that gel then ends up in the filter element. If that filter element is good enough, it'll hold that gel until you take it off for cleaning. If you're taking it to too high a pressure, it will eventually push that gel back through into your flow and end up downstream. So what we identified was a dead zone there. This is now showing you the outlet of that same filter vessel, and we identified 2 more dead zones on the outlet. One of them, again, a sharp corner in the actual manifold itself. And the other one is because they had flat tube sheets without any flow channels machined into them. And that was causing a buildup right on the exit at the top of the tube sheet. And those 2 spaces are doing exactly the same thing, except you've not even got any filters to capture any gels that get created and sloughed off, and indeed any hard particles that might end up getting sloughed off as well as carbonized particles. So that's just going straight into his film. So when we did the report for him, we actually included some of the work that we'd done in how we optimized. And this just shows you we've got 3 different optimization stages here, and we can do this utilizing the system. So we'll make a change, then we'll run it through the system again and just see how well that change worked. And what you can see is that we had to do 3 iterations before we got to what we thought was the best solution. We solved the inlet one on the 2nd iteration, but it took us to the 3rd iteration before we were happy with the final solution. And as you can see on the right hand side, we also one of the things we did was put some contoured flow channels, so we machined flow channels into his tube sheet. That's showing you a 19 candle system. His was actually a 7 candle system. But that's what we did with that. And just to report, the customer did tell us after he used this new vessel, so he kept the filter candles the same, but he utilized the new tube sheet and the new vessel, his gel count had dropped. So that was excellent news to hear as well. And one final slide, just showing by utilizing our CFD system for design of new systems, we can and one of the reasons we did this, won the contract for this system, was because this was the best designed system that the customer received. This I don't mind saying it, it's public knowledge. This was NatureWorks. They make a PLA polymer that does compete with PET. And this is the biggest system we've made. We did the whole thing. But we designed this system, and it turned out a completely different design than any competitive bid. And we were told it was by far the best design to give them the best performance. So we're really pleased with that, and we won the contract. We delivered it in July 2023, and you can see the details there, the viscosities and flows and such like. Very similar really to a large PET, virgin PET type system. And that is it. Thank you very much, and I'll pass back to Elsa.
Thank you, Paul. So let's go to Brian. So Brian, I'm going to stop sharing here, and you can share your screen, please. Thank you.
Okay, thank you. You can see that. I'll start the presentation.
Yes, we can see you.
I'm going to change it to a laser pointer, see how that works. Everybody see the cursor flying around?
Yes.
Okay, excellent. Okay, my presentation is called The Role of John Crane Filtration in the Energy Transition Market. Here we go. Today we'll be discussing the following subjects. We'll be discussing where filtration fits in to the energy transition areas such as hydrogen production, methane reduction, and carbon capture utilization storage, or CCUS. We will discuss in some detail the filtration products that fit into these areas. Then we'll summarize with some key takeaways. Let's look at hydrogen production applications first. This slide is busy. We won't go into the system details. We will look where the filtration applications are. So we have a typical coal electrolyzer system. In this case, it's a 50 megawatt electrolyzer where the electricity is supplied by solar and wind power. As the water is supplied by the pump here, it goes through a resin filter. This resin filter is it can be overcome by a high volume of dirt and could fill up fast. So the water needs to be filtered with a coarse filter in order to increase the life of the resin filter. Now the deionized water then is pumped into the electrolyzer. From there, we have hydrogen coming out here and oxygen coming out here. At this point, both gases can be filtered for both solids and liquids. Any water that is removed at this point can go back into the system, both in these high flow coal ester applications. Both then are compressed and then sent out into the market. The centrifugal compressors here and here will have lube oil filters and dry gas seal filters. So the hydrogen life cycle goes from hydrogen production to transportation and finally to end use. Filters are used throughout the cycle, including end use. The end use is a series of processes before it goes into the vehicle. At first, the hydrogen arrives as a liquid, either by tanker truck or pipeline. It must first be converted into a gas before it can be used. Here it passes through vaporizer towers that heat the liquid until it turns into a gas. Before the hydrogen goes into the vehicle, it must be compressed to high pressures up to 10,000 psi or 700 bar. There are two standards for hydrogen compression: half pressure, which is called H35 at 350 bar, and full pressure, called H70 at 700 bar. Higher pressure translates into higher range. On a modern fuel cell vehicle, such as the Toyota Mirai, for example, a full fill at 700 bar equals about 312 miles of range, which is on par with the gasoline-powered vehicles and electric vehicles. But hydrogen cars can be filled much quicker than electric vehicles can be recharged. The hydrogen sits in storage tanks at the source, just like gasoline, only above ground. To prevent expansion and to maintain energy density while being pumped into high pressure, hydrogen must be cooled through heat exchangers before it passes through the pump. Cooling prevents the vehicle's onboard tanks from overheating. Finally, the hydrogen goes to the pump to fill your vehicle. At this point, the hydrogen is filtered. It is essential that the hydrogen be very clean when it is in storage on the vehicle. The process that the vehicle goes through to convert hydrogen to power cannot handle any contaminants. One active project that we have is a major US-based operator of hydrogen liquefaction. The process uses cryogenic turbo expander compressors that use John Crane filtration for both lube oil and steel gas. Now we move to the subject of methane reduction. I know what you're thinking. How can a filter reduce methane emissions? We will be discussing how the seal gas filters protect the shaft seals on large centrifugal gas compressors and keeps them running efficiently. Centrifugal compressors used in the oil and gas industry are for applications such as gas injector compressors, pipeline compressors, natural gas processing, transmission, and storage. Centrifugal compressors use a spinning turbine to pressurize the gas. The rapidly rotating main shaft of the compressor is generally sealed with one of two technologies: the use of pressurized oil in a seal oil system, or the use of pressurized gas, either from the gas compressor is compressing or a second source, such as a pressurized nitrogen. So the wet seals is traditional technology that uses a system to circulate oil to seal the narrow gap between the shaft and the housing. This seal oil absorbs significant amounts of natural gas that must be removed from the oil before circulation. Typically, the gas is removed from the seal oil is directly vented into the atmosphere. That's why this old technology is one of the biggest contributors to methane emissions. This is the case for most worldwide methane emissions from compressors. The United States still has quite a few seal oil systems as well, but are being converted to the new technology, which is dry gas seals. Dry gas seals avoid the use of seal oil. Any emissions from dry gas seals can be sent directly to flare or back into the process, substantially reducing costs and substantially reducing emissions. These types of seals require very good filtration as well as coalescing of any liquids that can be found in the gas. The filter must remove solids and liquids from the gas stream before it enters the seal. Filtration leads to an excellent opportunity in supporting the dry gas seal retrofits that reduce methane emissions. Next, we'll discuss CCUS, or in other words, carbon capture, utilization, and storage. Along the carbon capture value chain, we have many opportunities to supply filtration. Pumps and compressors are used at every level of the value chain, and they need filtration to perform efficiently. Specifically, however, there are many opportunities for filtration during the carbon capture process. For instance, this absorption type process, the feed gas needs to be filtered as it's added to the process. And finally, the makeup solvent used to absorb the CO2 needs to be filtered as is added to the process. And finally, the CO2 is compressed using centrifugal compressor, therefore needing seal gas filters and lube oil filters at this point here. Even in the adsorption type system for separating CO2, filtration is needed. This system reduces the number of components that the absorption process uses. The adsorption column, however, is very sensitive to contamination liquids, therefore needing a high flow coalescer before the column. Also, the compressor at the end of this process needs the seal gas filters and lube oil filters. An application that we have experience with is one of the largest LNG projects that has CO2 removal and storage. There are 3 centrifugal compressors with John Crane Type 28 dry gas seals. These compressors will inject CO2 2 kilometers below ground. We are also providing seal gas filters and lube oil filter to support those compressors. Okay, what John Crane products will be used in the energy transition market? John Crane has all kinds of filter types for onshore, refinery, petrochemical, those types of filters would be lube oil, seal oil, hydraulic, seal gas, even fuel gas for turbines, water injection, demisters, and coalescers. Those evolved before the centrifugal compressors, reciprocating compressors, air compressors, gas turbines, and pumps. So first off, we'll present the lube oil filters that can be used on most centrifugal compressors. The type of filters that we provide are unique. They use a unique type of design, which is using forged materials rather than welded housings. This leads to more compact design with no welds, no weld inspection needed. All that's easy detection for dye penetrant tests and ultrasonic testing. No shrinkage during manufacturing, and a perfect seal using O-rings at the covers and at all the connections. Using design code can meet all international design codes around the world, including DOSH for Malaysia, CRN for Canada, AS 1210 for places like Australia. And of course, our main design criteria is the ASME Section 8, Division 1 for pressure vessel. Standard lube oil series starts around with a 1-inch filter, goes all the way to 8-inch filter, and that same bolted design, machine bolted design, is used throughout this whole filtration series. We do make a cast filter, and this is the start of our cast filter line, and this goes up to about 10 gallons a minute. And we're starting to release the larger filters now as we go forward. You could say that we'll discuss dry gas seal filtration. You could say that this is our forte, being in the dry gas seal market for 30 years. Early on, when dry gas seals were first introduced, late 1980s, filtration for these systems consisted of 2 single, what I call laboratory grade type filters, because they were basically the only coalescing filters available at that time. Unfortunately, the housings of these special filters didn't meet the stringent duty that's required for the API industry. What was needed was a filter to do the delicate coalescing work, plus have the rugged housing required for API applications. The housing needed to be an ASME design pressure vessel. It needed to have bolted covers, not screwed on bowls. It needed to meet pressure vessel standards from all over the world. It also needed to be duplexed together so the filter element can be changed out without shutting the system down. Hand valves can create a shutoff of gas if done incorrectly. A machined forged housing was the only answer. Indifil, a new company in the market, introduced this design early on in the 90s as a hybrid, you could say, which included the rugged housing, but also had the capability to do the delicate coalescing that these systems needed. It also had a zero leak transfer valve for duplexing the 2 housings, thus limited the hand valves. This design quickly became the industry standard for a good many years. Many filter companies followed suit, and this is a look of seal gas filters today. John Crane bought Indifil in 2008. John Crane has been in the filtration business ever since. We also added innovations such as a double block and bleed transfer valves. We could also add accessories such as sight glass level indicators, level switches, level and differential pressure transmitters, and other liquid monitoring equipment. Bolted design Machine design quickly led to many new innovations, such as this two-stage filter assembly that has a built-in knockout section, the first stage, along with the coalescing section on the second stage, and a single drainer vessel with its own transfer valve, so it will drain the filter that is in service. Within that vessel is an automatic drain that will drain the vessel when the liquid level reaches a predetermined level. There are two specifications that outline the requirements for seal gas systems and filtration. API 614, which is a lube oil specification that included requirements for seal systems, gas systems, because there wasn't a specification for seal gas systems in the oil and gas industry at the time. Required a duplex filter with continuous flow transfer valve, 4-micron absolute particulates filtration, 4-micron liquid mist filtration. It had to be sized for 3 times the flow and be less than 1.45 psi-d. API 692, which recently came out, is specifically for seal gas systems only. It became a stricter specification for filters. 1 micron absolute liquid and also particulate and also liquid mist filtration. This filter is to be sized for 3 times the flow, but across the entire filter housing, not just the filter element. All this innovation Indifil had was great, but now with the new API 692, we had to do something to meet tough sizing requirements. We needed to go to our production development team to redesign the filter to reduce pressure drop. This new design will lead to lower cost seal gas filters and in turn, lower cost of seal gas systems. The result of that development is the new John Crane FCF seal gas filter. FCF stands for flow condition filter. It's first of its kind to be designed using CFD software to reduce pressure drop to its absolute minimum. During this development, we discovered many innovations that put this filter at the forefront of technology. Using CFD software, we discovered that the gas at the point where it goes into the filter element is very turbulent and created a vortex. This vortex was causing a high velocity area in the element where the flow is concentrated the most. Unfortunately, this area is where the most liquid is draining on the outside of the filter element. High velocity area could cause some liquid carryover. John Crane developed a unique laminar flow technology to remove the vortexes from the gas flow. Additive manufacturing is used to create a flow straightener at the inlet of the element. This flow straightener here. This honeycomb design could only be created efficiently, that is, using this 3D printing. It became one of the first John Crane products to be produced by 3D printing for commercial use. The result is efficient use of full filter element media and reduced risk on droplet reentrainment. A decrease in operational pressure drop of 50%. For more information on all the innovations we discovered using CFD software, please send your comments or questions in the chat box. We can tell you that these innovations led to the best seal gas coalescing performance in the industry. Another filter identified in the energy transition market is our high flow coalescer. We have new, very high separation efficiency of 99.9% for improved equipment protection and process. Extended filter lifetime of greater than 12 months. Increased gas capacity of 450 absolute cubic meters per hour per element. And welded pressure vessel design reduces investment costs. We also use CFD software to design this filter to its absolute best efficiency. As described before, the hydrogen usage requires a special filter. We introduce our high pressure inline filters capable of 1,000 bar or 14,500 PSI. It can be installed on the hydrogen pump at the filling station and will filter the hydrogen before it goes into the vehicle. Same thing. As you can see, John Crane has a strong portfolio of filtration products to fit your needs in the energy transition market, and we have many ongoing projects right now and are poised to take on many more in the future. The landscape is changing, and we are ready for that change right now. So if you have any questions.
Okay. Brian Shackelford, did you have any additional comments here at the end before we close the webinar?
Sure. Let me say, for those who are attending, thank you, of course. And don't forget, if you liked what you heard today, be sure to register for the 2024 eChem Expo live event and golf tournament, Glenn, in April. You may do that online at echemexpo.com. Just click the registration button. Registration is free for attendees. And we look forward to seeing you in Kingsport during the 2024 Expo. And Elsa, thank you so much. And thank you for John Crane. And we really appreciate everybody's time today.